Hi, everyone, and welcome back. It's Kira Garfola with Math 155 at Greenville Tech. Today, we're going to finish off Unit 2 by talking about Section 2.6, which is measures of dispersion. So what is dispersion? In the last section, we talked about measures of central tendency, okay, so where that data centered or where most of the data hung out. But today, we're going to discuss measures of dispersion, which is kind of, if you're familiar with the word dispersed, how spread out those data points are. So central tendency talks about where they tend to cluster, and dispersion talks more about how far from that point they are. So how far around that center do they tend to lie? If we talk about central tendency and dispersion, we get a much more complete picture of the data. For example, if you consider the data set 1 in 100,000, and then you consider the data set 49,999 and 50,001. If you calculate the mean for those two data points in each set, the mean is going to be exactly the same. It's going to be 50,000, but you're going to get a very different picture, right? 0 and 100,000 are a lot more spread out from each other than the other two numbers are compared to each other. So our first measure of dispersion that we're going to talk about is called the range. And the range is a really simple measure of dispersion. You guys maybe have seen it in another class. You've probably talked about it before or known it in a non-math setting, right? The range mathematically is the largest value minus the smallest value. So mathematically speaking, we don't say, oh, well, the data set ranges from 100 to 300. We would say the range calculated would be 300 minus 100 in that case, okay? So for example here, we want to find the range of the numbers 7, 12, 4, 5, 7, 9, 17, 18, or 17, 8, and 8. Excuse me there. All we need to do to find the range is to find the smallest value and find the largest value. So here, our smallest value is going to be 4. And our largest value is going to be 17. So to get our range, it's just going to be the largest minus the smallest, which is 17 minus 4, which is going to give us 13. Now, let's practice with a few examples here. Let's find the range of each of these three data sets. So we have one here, and one here. In this first one, it's pretty easy to see that the lowest is 4. They're in order for us. That makes it nice, right? And the highest is 15. So our range is going to be 15 minus 4, which is 11. Okay. In the next one, we have maybe their salaries, they're somehow money values. Our largest is 100,000, and our smallest is going to be 18,000. And so our range is going to be the difference in those two, which is just going to be 100,000 minus 18,000, which is going to give us $82,000. And on the third one, there's a lot more numbers here, and they're not in order, okay? And we can actually use the calculator that we used in the last section. Those one variable stats. It'll tell us, it doesn't tell us the range, but it does tell us the min and the max. And so that can help us here. But if we look really carefully, it looks like our largest is going to be 99 and our smallest is going to be 49, I believe. Okay. So our range would just be 99 minus 49, which is going to be 50. Okay, so the range is pretty easy, pretty straightforward. Just remember on your test, when you're asked to find the range, I'm not asking for this first one. I'm not saying ranges from 4 to 15. I'm looking for the number 11, okay? Now the range is nice, but it's really, it's not always reflective, right? If you have some outliers or extreme values there, they can kind of give you a false picture of what's going on. And the standard deviation gives us a slightly better picture going on, although there's some statistical theory on why it's not always the best also. We'll save that for Math 120 if you'd like to take that with me also. So a more common measure of dispersion is what we call the standard deviation. And for some reason, students are terrified of this term, standard deviation. I don't know what happens to you before you come to my class, but if you have heartburn from hearing the term standard deviation, please forget about it. I'm going to show you how we're going to calculate it, and I'm going to tell you exactly how to get it in your calculator, and you're going to have to do very little of it by hand. The standard deviation is based on how far those observations are from the mean. So compared to that mean as the center, how far do I expect an observation to lie? If we want to calculate them by hand, we're going to use these formulas. Notice that the formula differs by sample. Again, we'll save this conversation for Math 120, or if you're particularly curious, feel free to send me an email, and I'm happy to have that discussion with you or explain it to you, but I don't want to bog down our lecture with irrelevant stuff. If we have a sample, we're going to be talking about this as the summation, okay? So we're going to take every x value and subtract that mean, and we're going to square that value, and then we're going to divide by n minus 1. So how many we have minus 1. And then we're going to take the square root because we're going to undo that squaring. The important thing for you is that we have S for sample, and this is a lowercase sigma for our population. Notice that now we have mu instead of x bar, and we have big N instead of little n. These are just notational differences between populations and samples. Now, if that formula scares you, don't let it. We're going to use our calculator to get these answers. I do want to show you how you could simplify it by hand if you wanted to. Excuse me. But basically, like I said, you're going to find each observation's distance from the mean, and you're going to square it. Squaring it gets rid of any of the negatives, okay? We're going to add all of these values, divide by n minus 1 if it's a sample, or n if it's a population, and then we take the square root of it to get the standard deviation, okay? If we want to find it by hand, the easiest way, hands down, is to create a table just like this. Now, I'm going to walk you through an example here, but I want you to not panic, not anything. I just want to show you how it works. Again, it's in your calculator in those one variable stats, and we're going to see that here in a minute. Let's find the standard deviation of the sample. We know it's a sample, so we're going to use the formula of S. 1, 2, 3, 4, 5. Okay, so our X values are 1, 2, 3, 4, and 5. We can quickly see, you can check it, making sure that you can find this, that our mean is 3. And now we find the differences. So X minus X bar here is negative 2, negative 1, 0, 1, and 2. Okay. Now squaring this column, we're going to get 4, 1, 0, 1, and 4. Again, you're not going to be expected to do this, but I want to show you where it's coming from. If we add up this column, okay, the sum is the same as that symbol. So the sum of this column is this entire numerator. So 4 plus 1 plus 0 plus 1 plus 4 is 10. So that means that this equation becomes S equals 10 over, how many do we have? We have N equals 5. So 5 minus 1, which is going to be the square root of 10 over 4. Okay. We can put this in our calculator, and it's going to give us somewhere around 1.58. It's not entirely difficult or complex, but you can see these are nice, pretty numbers, right? 1, 2, 3, 4, 5. There's only 5 of them. There are no decimals involved. But you could see if you had 100 numbers or 12 numbers, or you started to have fractions or decimals, it'd get really ugly really fast. So luckily, we can use technology. Now, if we want to find the standard deviation for our grouped data, it's going to be just like finding the mean for our group data, okay? We're going to have S still if it's a sample. And now we're going to talk about similar to that standard deviation, right? Of the non-grouped. We have each difference minus X bar, and we're going to square it. But now we're going to multiply it by its frequency. And then we're going to divide it by the sum of those frequencies minus 1. So that's still going to be N minus 1. But again, don't worry. Don't give anxiety. Don't anything over this one. We are not going to do these by hand. I'm not going to show you one of these by hand. Okay. In my entire career as a statistician, I've never had to do one of these by hand except in like my intro classes. You are not going to have to do any standard deviations by hand. We are going to use our calculator. Yay. The calculator is going to save us a lot of heartache here. Get your answers here in the calculator. You are going to take the exact same steps that you did in our last section to get your mean, median, and quartiles, okay? You're going to enter the data into the calculator. If it's a frequency distribution, you're going to put those in L2, and you're going to use one variable stats, okay? Something that is very important here is that you need to know, since that formula differs, that if you have a sample, you want to use SX. Okay, this is going to be most common. But if you know you're working with a population and you're looking for the sample sigma X, okay? So if I give you sample data and I ask you what the standard deviation is, then this is what you're going to be looking for. But if you know you're working with a population, it's rare that we always have everybody in the population. But if we do, you want to get that sigma X, okay? Remember that formula slightly differs. We divide by n instead of n minus 1. Okay, so we've found the mean and median in the previous discussion, but now we're going to use those same data sets to find standard deviation. Okay, so let's find the standard deviation of the numbers 4, 7, 8, 10, 12, and 15. If we want to do these, we need to open our calculator. And remember, we're going to press data twice to clear it. And then we're going to enter our data. We had 4, 7, 8, 10, 12, and 15. Okay. We're going to press second stat. And we want one variable stats. It's in L1. We don't have a frequency distribution, so we're good. And we're going to press calculate. We are going to assume that we are working with a sample here, okay? So assuming a sample, we see that our standard deviation is 3.88, okay? In fact, I'm just going to type it here. So 3.88 is our answer there. If we want to find it for these incomes, we're going to press data twice again and clear it. And we're going to enter 100,000, 42,000, 25,000, 20,000, and 18,000. We're going to go to one variable stats. Everything's good because we don't have a frequency distribution. And we see that ours is somewhere around $34,307. So 34,307.4. We want to do it in cents because that would probably make the most sense. 43, since we're talking about dollars, right? We're going to assume sample here. Okay, let's look at the next one. We want to find the standard deviation of all of these numbers. So we're going to enter these into our calculator the same way. Use one variable stats. It's a sample here, okay? So we know that we're looking for SX. If we do that, make sure that you can go back and do it as well. You should get the SX is equal to 10.36. Okay. Now, if we have grouped data and we want to find the standard deviation, let's assume it's a sample. Okay. Then we need to do the same thing in our calculator that we did with group data before. We're going to press data twice to clear it. We have 110 here, 140 here, 175 here, 200, and 250. Okay. But we also need to put our frequencies in here. So 4, 20, 15, 5, and 6. We're going to go back to one variable stat, but now we have a frequency distribution. So our data is definitely in L1, but now our frequency was in that second column. It was in L2. So we're going to make sure that highlights and press enter. And we're going to see that our standard deviation is about 39.2. Okay. Again, follow through, pause, do what you need to do to make sure that that makes sense. Now, if we want to interpret our standard deviation, basically a small standard deviation means that most of the data is lying close to that point, and a larger standard deviation means that it's more spread out. Okay. If you have a set of data that has a larger standard deviation than a set of data with a smaller standard deviation, you're going to think like, hey, that smaller standard deviation is less variable. Okay. The one with a larger standard deviation is more variable. You expect that data to be more spread out. So for example, Ben and Nate are in a biology class together. Ben's lab report scores have a standard deviation of 6.89, while Nate's have a standard deviation of 11.31. Whose scores do you think are more consistent? Well, remember, the consistent is not variable, right? So whose scores are more clustered around their mean? Well, Ben's has the lower standard deviation, so his fluctuate less. That would mean that his are more consistent. So here, Nate's are more variable, Ben's are more consistent. If we want to visualize standard deviation, we can see that these histograms are progressively larger standard deviations. With our first one, between 1.5 and 2.5, all of our data is clustered right there. Our data isn't very variable at all. So we have the lowest standard deviation from all of these right here. In B, we get a little bit more standard deviation because we're starting to see some data spread out a little bit. Not a lot of the data is spreading out, but it's spreading out nonetheless. In this one, we have more data spreading out from that center, right? It's still centered here, but our data is kind of pulling out further. We're getting more of them further from the mean. In D, we have what we call a uniform distribution, where they're all equally across. It's still centered technically around this mean, this middle, right? But our data, we have a lot of data on either side, half of our data on either side, and all the way spread out uniformly. Our standard deviation even continues to grow here because while the mean is here, the middle, right? Median, we're going to have all of our data is clustering further away from it. And so more data is further from the center than any of the previous ones. And lastly, with these two bars, our middle is still right here around 2. But all of our data is clustered at the furthest points away. There's no data clustered close to 2 at all. So A through F are increasingly large standard deviations. So in conclusion, make your life easier. Just like the previous section, use your calculator. Do not try to do standard deviation by hand. It gets ugly very quickly. I've been doing this a long time and I still screw it up. It's just easy. There's a lot of rounding error that can accumulate if you're using decimals. There's a lot of places to lose calculations or to make a mistake. Use your calculator. Double check that you've input the values correctly. You need to get some practice. Practice all of our measures of central tendency and dispersion with every single example that you see. I can give you data and I can ask you all of the ones that we've worked through, right? Remember, there's tons of examples in our text, tons of examples in the chapter, and the supplemental practice problems with solutions. You need to check your course schedule for assignments and test dates. This is the end of Unit 2, so you definitely have a test coming up. Use that practice test. Use the practice materials. There's even more practice there. Remember, if you need help, I am here at any time. The Math Center is available. Your textbook is always available, and there are extra resources and videos in Blackboard for supplemental instruction as well. Thanks as always for tuning in. Have a great day, and you're halfway through the material for the text.